Thank you for viewing this recorded Reliable Automatic Sprinkler Company webinar. Should you have any questions regarding this presentation, please feel free to contact Reliable Technical Services at 800-557-2726 or email us at techserve@reliablesprinkler.com. For upcoming webcasts and an archive of past webcasts, please visit reliablesprinkler.com/webcasts. Once again, thank you and enjoy the presentation.
Thank you everyone for joining us this morning. As always, let's start with the disclaimer. The views expressed today are the opinions of Reliable Automatic Sprinkler Company and may not necessarily reflect the views of the NFPA or Factory Mutual. So today we're going to talk about the basics of water spray fixed systems, those fun projects that come along every once in a while and take us away from the day-to-day routine of spotting sprinklers and joining pipe up in buildings. So I'd like to start by looking at why we have water spray fixed systems, and I kind of came up with 4 reasons for that. So here you can see we have a wildfire. Well, what does water spray have to do with the wildfire? Well, out in the middle of that wildfire, in the line of fire, if you'll pardon the pun, we may have things like this. Now, generally in a large industrial site, there's going to be setbacks and clearings and things like that to prevent that onrush of fire from creating havoc with this type of asset. But occasionally we do need to do something additional. So in this case, we're looking at not necessarily an issue that might arise within the tank setup itself, but more on the what's going to happen when that fire rolls into our environment. Now, just a couple things to notice as we look at these pictures. You can see these cylindrical horizontal tanks are protected, obviously, by the red piping routed around there. We're not going to get into the details of the piping. Now, one of the cool things about these type of systems is you get to be a little bit creative. You need to work with the various parties that are involved for supporting pipe and things like that. So it does lend itself to a little bit more flexibility and things like that. But just take a look at the pipe routing and things like that as we go through the pictures. And you're going to learn a couple of additional things that maybe aren't necessarily fire related. Also out in that environment, we may have something like this. This is a spherical tank. So why do we have spherical tanks versus cylindrical tanks? These are the fun things that I get to research and look up as I'm preparing these presentations. Spherical tanks have the benefit on the inside of the tank of having the exact same pressure across all surfaces. That's the good thing about this, the spherical tank. The bad thing about the spherical tank is they're very expensive to manufacture. Every piece of that welded shell is different. And if you want to change the size, then every piece of that shell has to change shape and be welded together. If we went back to the cylindrical tank real quick and look at that, we can change the capacity of that tank by adding sections along the interior, and then the curved shell space can just be moved out, and that allows us to adjust the capacity up and down very quickly. Now, the one thing that it does do is it puts more pressure towards the ends than it does on the side. So those are things that are taken into account when people are designing, what type of tanks to use that, and again, what's inside the tank. Again, here with the spherical tank, you can see that we have rings of protection, and you'll notice that at about the equator of that tank, the rings of protection become closer together. Obviously, that's because we don't have rundown past the equator, and we'll talk a little bit more about that. But again, here's a pipe routing, curved bent pipe supported on the stanchions of the tank. So again, just an opportunity to be creative. We're not going to get into the details of the systems in terms of their operation. Just think in terms of deluge systems, right? Electrically actuated, wet pilot, dry pilot, open nozzles typically. So we're not going to get into those details. That's a presentation that we've either had or we can do in the future. So a second reason why we had exposure from, let's say it's a wildfire. The second reason, 3D fires, right? A liquid fire that spills onto the floor. We talk about that when we talk about aircraft hangars. The volatile liquids running sideways and the need to then somehow attack those flames, and potentially from a much lower height than the sprinklers that might be at the roof, if there is indeed even a roof available. So what are we talking about in that case? I'm talking about things like oil-filled transformers. What do we have oil in a transformer for? Well, it's the same reason that you have antifreeze in your car. When you transform energy, it's never 100% efficient. And the loss that occurs due to that inefficiency is created in the form of heat. So we have to then cool the environment. Now, these transformers can be 90+% efficient, but there's always a need to remove some of that heat, and it's done very much the same way, again, as the antifreeze in your car. We have a large tank of oil. You can see it sitting up there on top. Around the about the midpoint up are a bunch of radiators and fans that are drawing air, running it through a system, again, just like your car, to keep that transformer cool. And once again, you can see the piping arrangement urgently painted red in a lot of these cases to identify it, but again, working its way around. And we're going to talk about further on in the presentation some of the requirements for these various types of protection schemes. So another reason why, well, oftentimes we're moving materials across areas that we simply can't get to. This is a very good picture of an elevated conveyor that happens to be in a pretty bad state at the moment. But not only do we have materials that are engaged in a fire that we can't get to, but they're also moving typically horizontally or diagonally up and down. Now we've got this case where we're actually moving a fire into potentially either into a building or another process application. So what are we looking at here? Well, typically we're talking about obviously conveyors. And again, here we see some piping that's routed over the top of the conveyors. This may or may not be on a deluge system at this point, and it's likely within a sprinklered building. But again, we're doing this very localized application to protect whatever asset that we're attempting to protect. And then the fourth reason, at least that I came up with, and there may be more, building collapse or structure collapse, right? We all know what happens when steel heats up. It loses its strength and it is prone to collapse. So this could either be building structure or the supports underneath a tank or underneath a pipe rack or a conveyor or anything like that. So we've got to protect those supports to maintain the integrity of whatever those supports are holding up. Now, in a building, obviously, most often we have passive protection, either in the form of some sort of wrapping with a non-combustible material or some sort of spray-on type monocoat affair. We don't typically see water spray systems used to protect building structure, although, in the case of upright sprinklers, we do get some benefit of steel protection or wood protection in that case. So as far as structure goes, not necessarily for the building structure, more for the supports of these various type of assets. So let's play a little question of what year did NFPA 15 debut, along with Mr. Bugs Bunny. So when you research headlines of 1940, it was very difficult to find one that was lighthearted. It was, as you can expect in 1940, all about World War I, or excuse me, World War II. So, I kind of had to dig a little bit, but I came up with this guy. 1940 is when the first edition of NFPA 15 was published. Makes it 81 years old this year, going on 82 years old. It's been around for a while. It's not undergone a lot of change over the last few years. It's pretty stable, as you might expect. It's built much like NFPA 13, again, as you also might expect, right? Chapters 1 and 2, administrative chapters. Chapter 3, definitions. Chapter 4, some general requirements. Chapter 5, system components, you know, the nozzles, the valves, the fittings, etc. Installation requirements in Chapter 6. But Chapter 7 is where we're really going to find the meat of NFPA 15. Chapter 7, and again, these are not everything that can be protected or are required to be protected. These are the most common. And in a lot of cases, like we have to do with special sprinklers and special system designs, we need to extract the appropriate parts of these maybe different types of protection and apply them to whatever it is that may be new that's come across our board. So, but for these typical common protection schemes, we're going to see things like cable trays and cable runs, belt conveyors, as we talked about, an interesting chapter or section called control of burning, which we'll learn really is related to open tanks of material. Exposure protection, again, those LNG or propane tanks sitting out in the field, for instance, structural steel we just talked about. We've got a section on pipe racks, tubing, conduit racks. We got a section on transformers, and then finally a small section on flammable vapor mitigation. So those will be the ones that we're going to touch on real quick. That's NFPA 15. What does Factory Mutual have for us? Well, Factory Mutual has adopted NFPA 15. Now, it says that right in the front of their data sheet 4-N1 that they have adopted NFPA 15, but as they are wont to do and have the rights to do, they've taken some things and moved them around here and there, and then they also give us some additional data sheets to work with. By reference, would reference us to transformers in data sheet 5-4, 7-11 for conveyors, 7-14 for chemical processing plants, and then 7-55. And these are just some examples for your tanks that are essentially in what we call stationary installation. So what's really the difference with the water spray system, right? Well, the primary difference is we're going to use a water spray nozzle. That's not to say we can't use a sprinkler, and we'll see how that's allowed in the standard. But you can see the definition on the screen. Everybody, I would presume by this point in their life, has held a nozzle at the end of a garden hose even. We should all know what a nozzle is and what it can do. We've all, hopefully been around fire sprinklers and realized that they're essentially a nozzle with a thermal element in it. But what does it do? It's used to direct or modify the flow of a fluid, in this case, primarily water. So there's your definition. So in that regard, right, by the definition, every fire sprinkler is a nozzle. It does exactly what the definition says. And there are some obviously fire sprinklers on the screen, but every nozzle is not a fire sprinkler. Not every nozzle is a fire sprinkler, I should say. And I tried to find out what type of argument that is, and it leads down a massive rabbit hole of logic and philosophy and all that. So don't go there. But every fire sprinkler is a nozzle. Not every nozzle is a fire sprinkler. Nozzles are tested and listed to a different standard, either UL 2351 or FM 2025. Whereas we should all know by now, fire sprinklers, the basic for UL is 199, and for Factory Mutual is FM 2000. So they have their own testing criteria. Obviously, we don't have a thermal element. We don't need to worry about activation times. Typically not worried about deflector distances and things like that as it relates to activation. But again, they are different creatures, and they're defined not very clearly. And all the research led back to this thing that, hey, the differences between these nozzles is kind of nebulous, but we have these general characteristics that we work with. So what are the types of nozzles? 3 types, basically: low velocity, medium velocity, and high velocity. On the left is a fire sprinkler. That is just a pendant, 1/2 inch, quick response fire sprinkler, knock the thermal bulb out and take the guts out of it, and it is essentially a low velocity nozzle. And you don't really find that referred to in NFPA 15. It doesn't say, hey, a sprinkler is a low velocity nozzle, but when you do the research, you realize that that's essentially what we're talking about. And then the other types, and by the way, NFPA 15 essentially says that you use open nozzles for protection. But similar to what we have in NFPA 13, there's a section that says where approved, sprinklers shall be permitted to be used in these systems and installed, and this is the important part, installed in positions other than anticipated by their listing. So what does that mean? You knock the guts out, and all of a sudden, does this sprinkler have to be pendant anymore? No, it doesn't. It essentially, because now it's a nozzle, it can be oriented in any position that's needed to accommodate the protection scheme. So sprinklers, low velocity nozzles, medium velocity nozzles. We'll talk about some of these characteristics here in just a second. And then what's called the high velocity nozzle there on the right. And obviously, much like sprinklers, we have these available in different K factors and discharge angles particularly. We don't have that ability necessarily with the low velocity fire sprinkler, but we do very carefully shape the size and the shape of the cone that's doing the protection out of these other two. So how do we select the nozzle? We select the nozzle, as you might expect, by what it is we're trying to do. So in the case of, let's say we're moving coal down a conveyor, I really don't need to throw a lot of velocity onto that coal. Let's assume that it's burning coal, and I don't want to blow it all over the floor. So we really want to throw enough water on that moving material, and that's typically done with, let's say, a low velocity nozzle fire sprinkler. If we're doing cooling, we're protecting from exposure fire, we have a little different mechanism of fire control, and we're going to typically use a medium velocity nozzle. And again, we'll talk about why that is here in a second. And then finally, for some of the heavier oils, we're going to use the high velocity nozzles. So let's take a look at the differences. We'll work our way backwards, back from the high velocity. These are typically characterized by small orifices. They're going to have half-inch threads, but the orifice and the bore and the taper and contour of the bore up through the nozzle itself is going to be relatively small. You're typically going to see individual strainers mounted on these, depending on the K factor. And depending if they're too small, you may need a mainline strainer installed on the system as well. So small orifice number one, high velocity, high pressure. Typically, you're going to see these in maybe the 60 psi to 100 psi range. More defined by the physical nature of it rather than the velocity. Those numbers even start to get a little bit confusing as you work your way back and forth. Those are more manufacturing properties rather than to say that, hey, if I throw 100 psi through a sprinkler, it now becomes a high velocity nozzle. No, that's not the case. It's the sprinkler, or it's the nozzle and the physical nature of it. Again, multiple discharge angles, the shape of the cone. In this case, you can't really tell from the end, the lower left end there, but interior there's got a taper to it, and as that water exits, it's going to be a narrow cone or wider. So multiple discharge angles, pardon me, and no deflector. Okay, so no deflector on these. The water is simply going to just exit through, and it's going to come through in pretty large water drops. We again have no deflector to break it up. And so what effect is this having on the fire? The large coarse water drops provide penetration down through the rising fire plume, but they also, and because they're under high velocity, they're hitting the surface, right? They're in close proximity. They're actually creating turbulence in the surface of the fuel. And what it's doing is the water is what they call emulsifying. It's mixing together, and it extracts the heat, and it dilutes that fuel down, and that's part of the firefighting process, what they call emulsification, the blending of two together, even for the period of time that it's being hit with the turbulence to affect that fire protection. There's some cooling effect from the drops, but we're going to see how the medium velocity nozzle has even a better way of doing that. And then finally, there is some smothering effect. But the main concept between the high velocity is that coarse water drop, flame and fire plume penetration down to the surface, boil that water. I hate, maybe that's the bad word for it, but let's activate that water and get the oils and the water mixing, the fuel and the water mixing to affect the firefighting process. So where are we going to see these used? High velocity nozzle applications, less defined by flame or by flashpoint, excuse me, than at least it seems when I was researching, than by specific gravity. So you can find tables that will give you the specific gravity of different oils and fuels and vegetable oils and all kinds of stuff like that. Medium to heavy oils, specific gravity of 0.85 or higher. So where do we see these? Again, in the transformer world, diesel engines, fuel oil storage tanks, bunker oil, things like that, and lube oil systems. That picture on the right that I came across there, interesting. I looked at it and I thought, wow, that's like some massive thing that's from, the 1920s. That's actually a radial diesel engine, which I did not know existed. But so it's kind of a very cool. It's on a water pumping station down in Florida on Lake Okeechobee or something like that. But I thought that was kind of a really interesting picture. So let's go to medium velocity nozzles. Typically larger orifices, right? How do we reduce the velocity? We open the orifice size a little bit. Moderate pressures, these are going to be in, let's call it the 20, 25, 30 to 60 range-ish. If you want to try to at least apply a number, think in terms of that. Again, multiple discharge angles. That discharge angle typically driven by the splitter cone and that deflector. And we'll see in a little bit. You got to kind of look carefully at it, but when you look at these nozzles, you'll see that those deflector tines start to flatten out or steepen, and that's the mechanism by which we shape that cone. And then finally, again, the internal deflector. So why do we use a deflector on a sprinkler to begin with? And the same reason we use it on the medium velocity nozzles is to break the water into the appropriate water drop size. It shapes and it breaks the water into much finer particles than it does for the high velocity. So what effect are we having on the fire? Well, the finer drops don't give us the fire plume penetration that we have with the high velocity. We're going to use these on lighter oils. Again, we'll see in a second, but lighter oils really don't emulsify, so it doesn't do us a lot of good to splatter the top of those oils. That the mechanism just doesn't work properly when the oils are a lighter weight. So the primary effect of the medium velocity nozzle is cooling. Okay, when you break the water into smaller drops, there is much more surface area available to absorb heat. A pound of water, which is about 1/8 of a gallon, absorbs 1,150 BTUs as it converts to steam. So it's gathering that heat that's coming off, and it's just simply cooling the environment down. When that water turns to steam, it then kind of starts wanting to drift downward, and it actually starts to kind of smother the fire. So you see a little bit of different fire protection process happening here with the cooling and the smothering. And then finally, in the case of vapors, we want to then take those water drops and start diluting and dispersing those vapors and get them out of the environment. So that's the effect there of the medium velocity nozzles. So again, where are we using those? We're using those on lighter weight oils, specific gravity around 0.85 or less. And where do we see those? Jet fuel, gasoline, kerosene, and again, medium velocity nozzle applications would be used again for that dispersion and dilution of vapors. So let's talk now about the common protection uses that come out of NFPA 15. Cable trays and cable runs, we're going to get into a little bit of details. We'll go through these pretty fast right here. 0.15 over every square foot application rate. So similar to sprinklers, we're looking at, square footage and densities. And so in that regard, the hydraulics, there's a section on hydraulics in NFPA 15 that I'm sure looks very much like NFPA 13. One of the things we want to do with these cable trays is pick up slow growing fires, right? We've got some wires that are shorting out or something's happening and things are increasing very slowly in speed. We want to pick that up very early on with this cable tray protection. If the cable tray is exposed to flammable liquids or molten materials above, we then go to the chapter or the section on exposure, and we're going to talk about that in a little bit. So just be aware if there's impingement from some fire hazard from above. And then in that case, we jump up the protection scheme to a 0.30 GPM over and under. And again, that's uninsulated, insulated cable where we have plastics and things like that, or non-metallic tubing exposed to a spill from above. So those are the basic rules for protecting a cable tray. Conveyors. We need to protect all the hydraulic oil areas. We need to protect the belt. And when you think in terms of the belt, remember you've got the belt on the top with the material on it. At some point at the end, it does a 180-degree turn and it comes back underneath itself. So when they say to protect the belt, they mean both the top and the bottom. Both NFPA 15 and Factory Mutual 4-1N will give you some really nice pictures of how to accomplish that, or some guidelines, I should say, on how to accomplish that. Obviously, the contents on the belt, and then whatever drive units are driving the belt. We want to make sure that when the fire system operates, that we shut down the equipment. We want to stop moving the burning materials if there are indeed burning materials. Very important that we stop that. So we're going to interlock that with the equipment shutdown. Minimum application rate of a 0.25 GPM per square foot. And then we also want to look at where this material potentially could end up. Is it going into another building? If so, that building needs to be protected. It makes sense, but they just have to give us the rules anyway. And then in probably more like an and/or situation, you want to automatically operate the next downstream segment of the protection. So if your system is zoned out, maybe it's by footage or whatever, when the fire sprinkler system operates, wherever that material is moving to that next zone downstream, we want to operate that system as well. So you need to be aware that you may have, much in the case of an aircraft hangar, more than one zone anticipated to operate at the same time, which obviously have an effect on your water supply and duration and things like that. So this next section is what they call control of burning. What is that? I thought we were trying to do that everywhere. Well, you see as we get through the requirements here, what they're after is an open tank, like an oil quenching operation or a cleaning operation for prior to painting, where you're dipping things down into liquid flammable materials and bringing them back up. So that's kind of what we're talking about here. So the system must operate until all fuel is consumed, or the flow of the leaking oil or whatever it is can be shut down, or the burning material is otherwise extinguished. So again, these are kind of some like really kind of nebulous concepts here, but it's apparently the best that we could come up with in terms of the committee language for these open tanks. Not less than 0.50 GPM for the equipment, which is where the fire is likely to be started. And then if the pool is just simply sitting there, we want to put a 0.30 GPM density over the top of the tank, or what they call the pool. Exposure protection. So again, envision the propane tanks, LNG tanks, whatever they are, sitting out in the middle of the field there. 0.25 GPM per square foot application rate. The spray patterns must meet or overlap. Now, this isn't in all the other sections, but if you think about it, it makes sense, right? You're going to look at the spray pattern. You're going to want to make sure there's no dry spots. But in this case of the exposure protection, is very clearly stated that the spray patterns must meet or overlap. Above the equator of the tank, no more than 12 feet on center. And again, down to the equator, you have what we call rundown, so you get some help with that. Once you're below the equator, we don't consider rundown, even though it's going to happen to a certain degree. We're not allowed to consider it anymore. That's why you saw in that spherical tank, the rings at the equator got closer together down at the bottom. It's a pretty easy concept to understand. If there are projections off the vessel, manholes, pipe supports, whatever they might be, you've got to look at those and consider whether or not the water is going to actually get to the underside of those. So look at the projections, make sure they're adequately protected. And then any uninsulated saddles that are supporting those tanks that are more than 12 inches high need to be protected, need to be looked at either in concert with the existing nozzles or perhaps with their own nozzles. So how do we do that? Well, interesting, it leads right into structural steel. Horizontal structural members, application rate of 0.10 GPM over the wetted area. Vertical members, not less than 0.25 GPM over the wetted area. And if an approved fire-resistant insulation is applied, again, we saw that in the terms of that monocoat, that can substitute with the approval of the AHJ, or some sort of a performance-based engineering analysis may substitute for the spray on the steel as well. Now, I do want to take an opportunity to share a little mistake I made in the contracting world years ago. It wasn't huge, but hey, who likes to lose money whenever it happens? This is the image out of NFPA 15. And I had a case where at the last minute, the fire marshal asked for fire protection on some exposed beams. It was in a Group 2 aircraft hangar. Maybe it was Group 3. I can't remember. And he said, "Hey, we got to protect those." So I got a change order to add, some sidewalls down one side of the columns. Well, don't be fooled, because what this doesn't show is that protection is actually supposed to be applied to both sides of that beam or that column. So I ended up doubling my head count on that. But again, just be aware of that. This went actually to, by behest of the AHJ, went to the NFPA EOD, and they confirmed that was, that was the intent, was to actually have it on both sides. Factory Mutual, and I'd like to give credit to both those organizations, actually gives us a little better picture of kind of what that should look like. This is out of DS 714, and they've actually incorporated a stagger, which in my opinion would be not a huge addition to the cost of the job, and actually a great improvement in the protection scheme. So don't make the mistakes that I made. Piping, tubing, and conduit racks. Interestingly enough here, we want the nozzles directed upward at the underside, unless it's not feasible. But where feasible, the nozzle should be directed up, pointing to the underside. There was really no language. I didn't have the handbook to understand why that is. I presume it's got something to do with, just something that's happened in the past. But in any regard, you're allowed to put it at the top if you have to. However, if you have multiple levels, the underside of the top level, regardless of what's happening above it, must always be protected. And then there's a table 74373, which gives you, it's not a very long table, but it says, for instance, if you have 6 levels, you protect the alternate levels with a 0.15. I'm not, don't quote me on those, but look at the table. It will tell you, do I have to do every level? If so, what density? Do I do every other? If so, what density? You've got some options in the terms of these multi-layered cable trays. And then finally, the nozzles at the underside, no more than 2.5 feet below the bottom of the rack. I did say finally, but there is one more, and it just kind of makes sense, right? If you're spraying at something and you're holding it up with a unistrut rack or whatever that is an obstruction, what they would ask you to do is just simply space within those within those stanchions or whatever they are, and you may need to protect them anyway. So again, space within the bays, and when you do that, obviously do it per the structural steel requirements. Transformers, complete impingement of all exposed exterior surfaces. Okay, pretty straightforward. But if you remember that picture we looked at, there's a lot of undulations and modulations in the outside of that. So these things need to be looked at, pretty carefully. No less than a 0.25 GPM per square foot application rate. The non-absorbing area beneath, these things are typically going to be sitting on concrete or on a concrete pad, so you're going to have a non-absorbing ground area beneath the transformer. You need to get nozzles down underneath there and cover that area that's down on the ground. Any space, again, talking about the modulations, the breaks in, the breaks out, up, down, all these things, any space greater than 12 inches needs to be looked at and protected individually. Transformers, by their nature, and again, you'll see the diagrams in both 15 and 4-1N, they take a lot of nozzles. They just take a lot of nozzles because there's a lot of different stuff going on that needs to be protected. As you're routing the piping, we want to make sure that we don't go across the top or across the face of what they call the transformer cabinet or any other areas that need access. That makes kind of common sense. The one thing that you'll find as well in both those documents is the distance away from for particularly energized parts of the transformer. In other words, if you have a I don't even know what the numbers are, 13.6 kVA or whatever it is, will tell you that your steel piping needs to be X number of feet away from that energized part of the transformer. So you got to pay a little bit of attention about how close can I be, because electricity and this piping don't mix all that well. And then finally, we do say complete impingement of all exposed exterior surfaces. Well, that's except the energized bushings or the lightning surge protectors. Those ribbed things that you see sticking up when you drive past the substation, those are what they call the bushings. So even though they're sitting out in the rain, when we discharge our fire protection onto it, typically the transformer hopefully would be shut down, but we don't want to create a case where there's so much water that we're direct shorting between these energized areas of the transformer. And then finally, again, just a small section on flammable vapor mitigation. I got to thinking about this morning. It's like, well, I mean, if you have it, it's pretty catastrophic. But I'm just imagining that there's probably a need every once in a while to emergency vent these tanks. And let's just say it's a heavier than air vapor, and we're going to put it in a containment pit. And if we have to do that, we want to make sure, or if it happens by accident, we want to make sure that we've got that adequately protected. So they give us some guidelines here. We want to make sure that we have automatic gas and vapor detection. Kind of makes sense. We want to make sure that we have, and we would probably have this in most cases with all of these systems, manual, local, and remote activation available to us. We want to analyze how long the length of material released might be and make sure our water duration is the same. We want to look at the individual areas, and perhaps for water supply reasons, it makes sense to cordon some areas off and make different systems. But again, we look at the protected area in terms of square footage, and that's our design area. And then if we have known leak points like valves or vents or things like that, we just need to look at those and have protection adequately applied to those areas. So that was all a lot of NFPA 15 stuff. Again, most of that is replicated in NFPA or in Factory Mutual 4-1N. But Factory Mutual has some kind of interesting stuff, and I hate to say it's a little bit of a hodgepodge, but I just kind of went through and just pulled in some additional stuff out of 4-1N. 4-1N allows water spray systems to be used for wall and floor opening protection. So maybe you've got a 2-hour wall between areas of a building, but you've got a conveyor running through it, or whatever it is. FM allows you to look at that and gives us some guidelines on how to protect those openings between floors and walls within the confines of what we're talking about today. This was interesting. It doesn't say that Schedule 10 or that Schedule 40 is required below 4-inch, but what it does say is you're allowed to use Schedule 10 for 4-inch and larger. So kind of by default for Factory Mutual, at least if you're bidding work, keep this one in mind that you're going to be looking at Schedule 40 for some of the smaller size piping. They do give us some guidelines on minimum starting pressures. These may be revised in the let's say you go to the transformer, it may say minimum 50, I don't know, but they do give us the minimums here in 4-1N, minimum of 20 PSI. Unless we're outside and we have small orifice nozzles, we want to drive those up to 30 PSI. The reason for that is wind. We've got to consider what's going to be happening out in the environment. Is there great, perfect tables and all this stuff in NFPA 15? I don't count on it. Some of this you just have to kind of think about what the environment is. If you're in Ellensburg, Washington, where the wind blows 40 miles an hour every day of the year, that's one thing as opposed to another location where it's pretty calm. 20 PSI over open tanks with high flash point liquid, such as a quenching oil. Quenching is interesting as you're looking through this. If you're not familiar with it, you form a piece of metal. It's red hot. You would think dipping it in oil would be kind of the last thing that you want to do. But quenching oil is put in a tank. It's heated, and what we're trying to do is slowly cool the piece of metal. And this is used in hardening efforts to make the materials hard. So for gears, truck gears and things like that, they use quenching oil, and they control how fast or how slow that piece of material cools down, and that all aids in the hardening. 30 to 100 PSI for kerosene and similar liquids. These might be like your cleaning solutions that you're rolling materials in and out of. We got to make sure that we protect against fires with those. And then finally, with these pool fires, the protection scheme, FM would ask you to extend it 10 to 20 feet beyond the outer edges of the tank in case it boils over and starts running across the floor. So those are just kind of some additional FM requirements. So now let's talk about some reliable products. I don't know if we have any UFC fans on there. Bruce Buffer, sometimes this guy's announcements are much more exciting than the fights themselves, but let's just say that introducing fighting out of the red, white, and blue corner, fighting fire that is, the reliable MV nozzle. This is a relaunch of a product we've had for a while, a redesign with some all new assets to go along with it that we hope are going to help you. You're going to see these deployed on the website, bulletin number 106. If you were to print this, it would be a relatively thick bulletin. And that's because we've given you flow charts for each sprinkler, or for each nozzle in different orientations. We've got 8 nozzles, 8 discharge angles 8 cone shapes, let's call it, coming off the deflector. And we've told you how to position those 9 different ways, from 0 degrees pointing straight down to 180 degrees pointing straight up. 9 positions around the one half of the clock gives us 72 charts of flow charts. Again, document number 106, going to have some additional information on it, dimensional, K-factors, finish, and things like that. I would like to point your attention to the notes that are on the bottom of page 2 and look at a couple of those real quick. Number 1, as I mentioned, these nozzles can be oriented in any position. Number 2, we just talked about. The spray pattern is shown is for discharge pressures between 20 and 60. So between 20 and 60, medium velocity, if that's what you want to call it, the cone shape stays pretty stable. Now over 60, the cone shape may start collapsing a little bit. Under 20, and we may not get the kind of breakup of water that we're looking for. So we're in that 20 to 60 psi range. On the chart, we'll look at one in just a second, what we call the transition distance. So the water exits the nozzle, energy carries it a certain distance before gravity overcomes the energy and starts pulling it back toward the earth. That's what we call the transition distance. So at a certain distance out, if you were to look at a cross section, it would be a perfect circle. As some of the water starts falling off the front, the shape, as you look through that cross section, is going to change. And so I'm going to show you in a little bit how we're going to account for that in your design. But that is what we call the transition distance. You can use it beyond the transition distance. Okay, this is just a reference point. So don't think that, hey, I can't go beyond, 3.5 feet, because you can. You just need to look at what the water's doing at that point. Again, number 6, these spray patterns were obtained from tests performed in still air. So you must consider the effects of wind and then obstructions. You are not going to be able to go to NFPA 15 and find obstruction tables like you do in NFPA 13. It's just not going to happen. So you need to look at those individually and do some engineering analysis on obstructions. So here is one of the figures, one of the 72 figures, 2-dimensional flat, looking at the side of this nozzle as it's spraying. This is a 65-degree cone, and it's set at 45 degrees off of 0, which again is pointing straight down. So imagine this thing, the next one would be 60 degrees, 75, 90. It would work its way up around the right side of the clock. And that's what generates these 72 charts. And are you going to need the charts? Perhaps, and we'll show you why I say perhaps in just a second. But let's take a look. That yellow line you can see is what we call the transition distance. It's in this case 3.5 feet before gravity grabs it and starts curving that water downward. And we've set all of these, the coverage at the bottom of these at 10 feet off the floor. What's happening at that point? Everything's going vertical. Would there be a need to set this 18, 20 feet off the floor? Not likely, right? So you're typically going to be having your asset protected within that hatched area right there. So these are going to be deployed to you, available to you, the designer, in a matrix on the website as individual 3D blocks. Okay, individual 3D blocks. All 72 of them are shown there. It's in a nice matrix. It's not a very large file. You grab this, pull it onto your CAD file that you're working on, and start playing around with these. And we're going to show you real quick what this kind of looks like. Again, just a reminder at this point, because it's convenient. We've done a nice job, Reliable has, over the last couple years in getting many more design assets available for you guys on the website. If you haven't noticed, go and look at the valves, the DDV, the deluge valves, alarm valves, the DDX, the FX dry valve. All of those now available in 2D, front, side, top, all the views you need, available individually as a 3D block to be pulled onto your drawing as well. So again, I just want to remind you that we've got all of those assets available for you, and now we've added this really cool, what we think is a really cool way to look at a design. So I'm going to play this little video, and we're just going to let this run here, and I'll just kind of narrate it. You can see at the top we got a 140-degree angle or a nozzle, and it's set at 60 degrees. So it's kind of up there at about the 10 o'clock position. You can kind of see the nozzle, and then the blue shading is the 3D block. That graph is on its own layer, so that can be turned off, can be left on as well. So what we're going to do here is now we're going to bring in a tank. This is just again, just a pretty rudimentary design, but you got a little tank, and now using my 3D tools that are available, we're going to draw this thing, we're going to pull it in and start looking at the effects of these nozzles on the tank protection. Here we're set off to the side, not doing us a lot of good, probably wasting a lot of water on the ground, and we're quite a distance away. So let's take the tank and move it, I think is going to be what we do here rather than the nozzle. Let's just drag that tank in, and now you can kind of see, you know, the block of water, so to speak, as it's hitting that tank and what's happening with it. So again, in most cases, you would probably isolate that that graph that's on there. It's just part of the block that's there. And we're just looking at a single nozzle right now. We're going to move this nozzle over the tank, or the tank under the nozzle a little bit in this case, go back to our 3D orbit, and now we can see what that water is doing across that tank. So we made these a little bit transparent. The idea here, guys and gals, is that you would take this, if need be, to your engineer of record or to the AHJ. It's a little difficult to see what's happening with these things in a 3D world looking at a plan. It's just tough to do. So you could take this and create a 3D PDF. You could do a Teams meeting with the AHJ and just show them where these nozzles are and how they're laid out and how they overlap and the coverage area and things like that. So there you can see the designers just essentially placing these nozzles around the tank. I'm going to grab a 3D orbit again and show you exactly what this thing looks like as we move around the tank here. So let's take just a couple minutes. We're almost done. We're going to let this one run. It's a similar video, but this is a little more elaborate. There's our tank. We're going to go through, and the first thing we're going to do is turn on our opening up some layers here, and we're going to turn on our nozzles. It's a little difficult to see, but as we zoom in, right down there is our nozzle. Okay, and then we're going to go turn all the nozzles on, turn the piping on, turn the fittings on, and we're going to see what this layout looks like. Does it have to be done like this? Nope. As I mentioned at the beginning, the piping layouts essentially can look anything that's needed to work out in the field. You're a lot of times going to see bird caging and grids and loops, and that's because we want these nozzles typically all discharging very closely together in terms of pressure. And a convenient way to do this, as we all know, and do it efficiently, is to do bird cages, loops, grids. It helps keep the pipe size consistent, which is important in terms of hangers and things like that. Minimize the number of sizes of couplings and clamps and all that stuff that you have to send out there. So you can see as we're working our way around here, we just select different nozzle discharge patterns, orient them at different orientations, straight down to the side, up from the bottom, and again, you can then essentially look for gaps in your coverage area, very easily shift things around, make sure that the flow is doing exactly what it needs to do. These models were all created in our flow lab with reference points set up. We know exactly what these nozzles are going to do and how they're going to do it, and that again was the origin and the genesis of these 3D blocks. So real cool tool that we hope you guys are going to like. And with that is at 2 minutes before the hour, the presentation. Do we have any questions out there, Brandon?
One in the chat right now asks if those spray pattern files are available in Revit.
I have no idea what Revit is. I'm sorry. No, I'm kidding. No, at this point they are not. And quite honestly, quite honestly, I'm not sure how Revit is used in the drafting process itself. Now, I'm not talking about, I understand that Revit captures data and things like that, but in terms of actual making a drawing and making this 3D visual tool to be able to show to people, I'm not sure what the realities of Revit is with that. Now I understand there could be a 3D block that has the nozzle information linked in it, maybe the densities and things like that. But at this point, it's the answer to is no Revit at this point. But we'll certainly consider it. Was that the only question?
That was the only one. Nothing else has come through.
All right, well, appreciate it.
Wait a minute, I'm sorry. There is one now. How does wind affect spray pattern of the illustration?
So that would take a much more powerful computer than we have at our hands right here anyway. I don't doubt that there are supercomputers, maybe not even supercomputers at this day and time, that could analyze the wind effects. Even if there were, it couldn't be published in terms of like an NFPA 15. There are so many variables that would be involved. There may be some guidance that could be provided. Hey, if the anticipated wind is 15 miles an hour, cut the spacing down by this much, or whatever it is. I didn't come across anything like that. It's simply that it must be taken into account. So this would be a case where you would probably have to get together with, maybe the AHJ for sure, maybe somebody in meteorology. I don't know the answer to it, but let's just suffice to say that the wind will probably be blowing, and it needs to be accounted for. Now, remember also that these nozzles aren't typically 12 feet away from the surface. Right, the nozzle you saw in the case of the cable tray or the conduit runs was within 2.5 feet. So a lot of times these things are going to be 3-4 feet away, and the velocity coming out of the nozzles is going to be such that windage might not have that much effect at all. But it needs to be considered, but to what degree is an answer that's not going to be found, at least to my knowledge, in NFPA 15.
Understood.
All right, well, go ahead, Brandon.
There is an additional question.
Sure.
Is the MV spray nozzle available in stainless steel?
Yes. No. I say yes because it could be if it were needed. It's available in plain brass, and it's available in brass with an ENT PTFE coating, which is a very, very good coating on its own. However, if the right circumstances were to arise, getting the nozzle in stainless is not far out of the realm of possibilities. When you take a nozzle that doesn't have activating elements and lever arms and thermal bulbs and links and all that stuff, it's not a big challenge to go to UL and say, can we make this out of stainless steel? Obviously, we have to run it past them, but the reality is, for the right project and perhaps in the future, getting to stainless steel, not at all difficult to have happen. But brass by itself is not a bad material unless it's in some sort of a caustic atmosphere, so to speak. But then if that's the case, then the PTFE coating, which includes the waterway, by the way, is another good option. And I didn't mention, but these are available with a blow-off cap as well. So you can protect the opening against infiltration of insects and salamanders and things like that. Those little critters get in small spots. So. Is that it, Brandon?
That appears to be it, sir.
All right. Well, thank you again, everybody. Appreciate your time this morning.